Hello! You're now listening to the Chem Mysteries podcast, where we dive deep into the fascinating world of chemistry. I'm Alan Jerry Sevilla, your host, along with my brilliant co-hosts, Cristel and Rodeline.
Hey everyone, I'm Cristel, your chemistry enthusiast here, ready to explore the mysteries of molecules and atoms with you.
And I'm Rodeline, super excited to take this journey with you all as we break down the wonders of chemistry and hopefully make this less intimidating and even fun.
In this episode, we're excited to bring chemistry to life for you. Now, before you hit pause, I'm begging you, please don't run. Stick with us for a few minutes, and we'll convince you that this isn't some torture subject, but a truly amazing science. Chemistry is not just a subject, it's a key to understanding the world in a way that will blow your mind and honestly make life even more enjoyable.
Right, chemistry is so much more than memorizing formulas. It's the bridge between the mystifying worlds of particle physics and biology. It has answers to questions we didn't even know we had.
And here's the kicker. Once you start to see the world through the lens of chemistry, you'll realize it's not about atoms and reactions. It's about seeing life in a totally new way.
So, are you ready to dive in? Buckle up! In today's episode, we'll start with one of the biggest ideas in science that everything is made of atoms. Let's explore what this means and take it from there. Welcome to Chem Mysteries. Let's unravel the wonders together. I know. You've heard this a million times, right? Atoms make up everything. But back when the atomic theory was first proposed, it sounded outrageous. And yes, we call it atomic theory still. Using the scientific definition of a theory, it's a well tested explanation, not just a guess.
That's right. Nowadays, no one's saying atoms are just a theory, thanks to groundbreaking work by Einstein. But did you know that atoms were only a hypothesis until the early 20th century?
Exactly. Robert Brown observed pollen grains dancing in water in 1827, something that scientists struggled to explain for years. Then, in 1905, Einstein wrote a mathematical model showing how tiny, unobserved particles were colliding with the pollen, proving the existence of atoms and molecules through something called Brownian motion.
And that's just the beginning. The concept of atoms goes all the way back to ancient Greece. A philosopher named Democritus thought that if you kept cutting a material in half, you'd reach a point where it couldn't be divided any further. That indivisible part he called atomos, meaning uncuttable.
Fast forward to the 1800s, and we have John Dalton, who took this ancient idea and proposed the first real atomic theory. He suggested that each chemical element is made of small, indivisible atoms that cannot be created or destroyed. He also proposed that all atoms of an element are alike in mass and properties, while different elements have unique atoms.
Although some parts of Dalton theory have been proven incorrect, like the idea that atoms are indivisible, his theory laid the foundation for modern chemistry. For instance, he explained the law of conservation of mass, which states the matter cannot be created or destroyed, and the law of constant composition, which explains why compounds have unique, fixed ratios of elements.
So, as scientists conducted more experiments throughout the 19th and 20th centuries, they discovered subatomic particles, the protons, the neutrons, and such. Through groundbreaking work by Faraday, Rutherford, and Chadwick, we came to understand that atoms aren't indivisible after all.
And now we know that these subatomic particles have specific roles in the structure and behavior of atoms. Protons are heavy and positively charged, neutrons are similar in size but have no charge, and electrons are tiny compared to the other two and have a negative charge.
Protons and neutrons make up the dense nucleus of the atom, while electrons orbit around the nucleus and play a major role in the chemical reactions.
Here's an important part, so stay with us. The number of protons in an atom determines what element it is. For example, an atom with 79 protons is always gold, while one with 47 protons will always be silver. This number is called atomic number and sits at the top of each element's box in the periodic table.
And this atomic number is basically the soul of the atom. As long as an atom has the same number of protons, it will remain the specific element, no matter what its electrons are doing or what it's bonded to.
Neutrons, on the other hand, don't affect the identity of an element, but they do contribute to its mass, leading to different isotopes.
But of course, chemistry doesn't end at the nucleus. Electrons, though much lighter, are the real star when it comes to the magic of chemical reactions. So, understanding the nucleus is just the beginning. Once we understand the nucleus, we start to unravel how atoms interact to form the complex molecules that makes up everything around us.
Exactly, and that's where we'll head next. So if you ever wonder what's really behind everything you see, stay tuned. Understanding atoms and their structure opens up a new whole world of understanding and appreciation for the incredible universe that we are part of. Now that we have covered atoms and their structure, let's move into the next piece of the puzzle, the chemical notation. After all, if we're going to understand chemistry, we need a way to talk about these atoms and molecules.
Right. Chemical notation is like the language of chemistry. It's how scientists communicate what elements are in a substance, how many atoms are involved, and how those atoms interact. Imagine trying to write a recipe without knowing how to list the ingredients or measurements. Chemical notation gives us that essential structure.
It's also a time saver. Instead of writing out two hydrogen atoms and one oxygen atoms, chemists can just write H2O. It's the shorthand that lets us quickly understand what's happening at the molecular level.
Exactly. So think of chemical notation as a way of translating the physical world into a language that we can all understand no matter where we are in the world. Each element has its own symbol like O for oxygen or Na for sodium, and when we put these symbols together in specific ways, they represent different molecules and compounds.
Plus, there's a lot of information packed into each notation. Take water H2O for example. The subscript 2 next to the H tells us that there are two hydrogen atoms bonded to one oxygen atom. Without chemical notation, chemistry would be a lot harder to follow.
And beyond just telling us what atoms are in a molecule, notation can even hint at how they are bonded and the types of reactions they can undergo. It's like a blueprint for the molecular world.
Exactly, Rodelin. And the chemical notation isn't just useful for simple molecules. It can also describe complex compounds, ions, and even reactions. In the next segment, we'll dive into the different types of chemical notation, symbols, and how chemists use them to express these ideas with precision. So let's get ready to decode the language of chemistry.
For example, let's talk about carbon dioxide or CO2. We write it as CO2. But what does it mean? It tells us that each molecule of carbon dioxide contains one atom of carbon and two atoms of oxygen. Pretty simple, right? But imagine trying to describe every single molecule without this shorthand. You would need paragraphs just to explain the air you're breathing. With chemical notation, we can communicate all this in just three characters.
Yeah, and speaking of the air we breathe, let's talk about another important molecule, O2, or molecular oxygen. This is the oxygen we inhale every second. But did you know that oxygen usually exists as a pair of atoms, not just one? If oxygen existed as single atoms, it would be dangerously reactive. By bonding together, the two oxygen atoms form a much more stable molecule, and that's why O2 is safer to breathe. So the O2 notation not only simplifies things, but helps us understand molecular stability in a real world condition.
Exactly, Alan. Chemical formulas are like recipes for creating substances. Take caffeine for instance. Its formula C8H10N4O2 reveals it's made up of carbon, hydrogen, nitrogen, and oxygen. That little molecule is responsible for keeping us all awake during those late night study sessions. Thanks to chemical notation, we can break down its composition and see why caffeine has the effect it does.
Yes, caffeine for life. And speaking of things that keep us going, glucose or C6H12O6 is the sugar your body uses for energy. It's in everything from fruits to candy bars, and it's basically your body's fuel source. Without glucose, your cells wouldn't be able to function properly. It's like the gasoline for our bodies. Even athletes depend on glucose to perform at their peak.
And let us not forget about ionic compounds like NaCl or sodium chloride, better known as table salt. Unlike molecules like H2O or CO2, where atoms share electrons, NaCl involves the transfer of electrons between sodium and chlorine, creating charged particles called ions. These ions give the salt its crystalline structure and make it dissolve easily in water. Ever wondered why salt water conducts electricity? It's because the ions in NaCl are free to move around when dissolved, allowing electric current to pass through.
And did you know that salt or NaCl has been so valuable in history that it was even used as a currency? That's where the word salary comes from. Roman soldiers were sometimes paid in salt.
Here's another fun fact. Did you know your body depends on sodium and potassium ions to transmit nerve signals? Without these ions, your muscles wouldn't contract and your heart wouldn't beat. So, chemical notation doesn't just describe abstract molecules. It's also directly related to how our bodies function and stay alive.
Exactly, Rodilyn, and that's why chemical notation is so powerful. It's like a universal language for scientists, helping us communicate complex information clearly and concisely. If you see NaCl, you know instantly that we're talking about sodium chloride or table salt. The notation helps you visualize what's happening on a molecular level. Sodium, Na, and chlorine, Cl, come together, exchange electrons, and voila! You have salt.
Right. It's kind of like learning a new language. Once you get a hang of it, it opens up a new world of understanding. The chemical notation allows you to break down the most complex substances, from your morning coffee to the fuel that powers rocket ships.
It's like solving puzzles. Understanding these basic concepts helps you tackle more complex topics later on, whether it's balancing chemical equations or diving into biochemistry.
And trust me, once you get into the practice with these basics, chemistry starts to make a lot more sense and even become kind of cool. You start to see chemistry everywhere and everything you do, and you realize how it shapes the world around us.
Isn't it amazing how much information you can get from just a few letters and numbers? Once you get familiar with this language, you will see how powerful it is in both understanding chemistry and applying it to everyday life.
Exactly, Crystal. And it's not just about the notation. These atomic interactions shape everything we see around us.
We now understand the atom and structures. We also have a good foundation for the chemical notation. We can go beyond the building blocks of everything we can see and look what they actually form, but that's another story for another day. Once again, I have been Alan Jerry Sevilla.
Crystal Joyce G. Esteves, Rodeline Angel Navarro, and to our listeners,
Thank you for joining us on Chem Mysteries. We hope that you feel inspired to continue exploring and questioning the world of science around you. Until next time, keep observing, stay curious, and remember, there's a world of chemistry out there just waiting to be discovered. Catch you later!